Hi, so today we're going to take a look at sequences. I got two parts to this video, maybe three, depending on how long this goes. But first thing I put up here is a little definition for a sequence. I wrote a sequence is a list of numbers written in a specific order. So it's not the sum of the numbers, it's not the product of the numbers, it's just a list of numbers written in some specific order. So I might write it like this. I might write out the a sub n's like this with the fancy brackets, which are a little bit tough to write on this pad here. I could write it as a list of a sub 1, a sub 2, a sub 3, and then keep going until I get to some nth term. Now, if I stop it there, then I might refer to this as a finite sequence. Finite meaning that it has an ending. So if I had 10 terms or 11 terms or 12 terms, that's where it would end after that certain term. On the other hand, I could come up with a sequence that starts with the first term, and I might list it as a sub 1, then a sub 2, then keep going to a sub n, and then keep going after that. So that sequence of terms has no ending to it. So instead of a finite sequence, I might refer to that as an infinite sequence. So the terms just keep on going and going and going. So some of this you might have seen before, but let's take a look at a couple of examples. This might make us feel a little bit better as we start this new chapter. So if I start looking at a sequence of terms that looks like this, I got 1, I got 5, I got 9, 13, and then this is just going to keep going. There's no end to my sequence. This one has a certain pattern to it, right? I can look at this right away, and I might refer to this as an arithmetic sequence. Arithmetic meaning that it has some constant difference. In this case, the constant difference is 4. So I started the first term, and I'm adding 4, I'm adding 4, I'm adding 4. Well, there's got to be some way to represent this besides just writing out all the terms forever. So I might try to look for a formula of some sort. The simplest formula to write, but a harder one to use, is what we call a recursive formula. I think your textbook calls it a recursion relation. So if I write a recursive formula, I need to know two things to write a recursive formula. I need to know where to start, and I need to know how to get to the next term. So where I start is my a sub 1. When I say sub, I'm referring to that little subscript that's down the bottom there. So a sub 1 is my first term. So in this case, my first term is 1. And then the next question is, how do I get to the next term? Well, the second term is just going to be the first term, add 4. The third term will be the second term, add 4, and so forth and so on. So in this case, I'm going to want to jump right to the nth term. So the nth term, whatever term you're looking for, is the term before it. So the term before it would be a sub n minus 1. If my current term is a sub n, my previous term is a sub n minus 1. And then tell me what to do with that previous term. Take the previous term and add 4. Now, I guess I should make a couple of comments about this. One of them is that those n values can only be positive integers. So I can't have a 1.5 term or a 1 3/4 term or a negative second term. That wouldn't make sense. Every once in a while, you'll see them written as a sub 0 as the first term. Yeah, you could do that too. So I might say that this is true where n is an integer value and n is greater than or equal to 1, because I've already specified what to use for the first term, so that formula there then works for the second term, the third term, the fourth term, and it keeps going. Now, the downside of that formula is, what if I want the 375th term? To find the 375th term, you've got to find the previous 374 in order to get to that. So instead of a recursive formula, I might also look at another type of formula that we call an explicit formula. An explicit formula takes a couple of steps to get together, but then if you want the 374th term, you just throw the numbers in. So the explicit formula specifically for this arithmetic sequence looks like this. The nth term is the first term plus n minus 1 times d. Now that d is going to be the constant difference, whatever it is between the terms. Now if you look at this, this might not look shockingly different from point slope form for a line. And it's not, right? That constant difference is just the slope, and now you're back to basically your y minus y1 equals the slope times x minus x sub 1, except now we're restricting those x values, or in this case the n values, to be integer values only. So how can we set up an explicit formula for our little sequence that we had here? Remember, it started with 1, 5, 9, and so forth. So here, our first term is 1, so a sub n is going to be 1 plus n minus 1, and the difference between each term we said was 4. So let's see if this works out. Let's simplify this a little bit, and I'll get 1 plus 4n minus 4, and then I can simplify that one step further and make it a sub n equals 4n minus 3. Now, does this work? Let's try it. If I put in a 1, right, I'll come over here, my a sub 1 will be 4 times 1 minus 3, and yes, that matches up with the first term of my sequence. The second one would then be 4 times 2, which is 8 minus 3. 8 minus 3 is 5. This is looking good so far. Let's try one more. My a sub 3 is going to be 4 times 3, which is 12, minus 3 is 9. Okay, so that looks like a decent explicit formula for my arithmetic sequence. Great. Let's try another sequence. All right, so this time, here, can I change colors? Let's try this. So this time, my a sub n's will be the sequence that goes like this: 3, 6, 12, 24, dot, dot, dot. Okay? All of a sudden, this thing is not arithmetic anymore. I'm not adding the same terms over and over. In fact, this time it looks like I'm multiplying the same thing over and over. So this thing is not an arithmetic sequence. This thing here is what we call a geometric sequence. Okay, and a geometric sequence has a constant ratio. And we use r as that constant ratio. So in this case, that constant ratio is 2. I don't know what that funny thing just happened there, but that should be a c. It should be a constant ratio. So let's try to figure out a way that we can write this formula for our constant ratio in two ways. We can do this explicitly, or we can do it recursively, or as the book calls it, a recursion relation. So recursively, well, it looks just like the one we did up there, except that instead of adding the same thing, we're going to multiply the same thing. So again, I need to define what my first term is. In this case, my first term is 3. And then the next term is 3 times 2, which is 6. 6 times 2 is 12. 12 times 2 is 24. So I'm always multiplying by 2. So how do I say take the previous term and multiply it by 2? I say take 2 times the term before it. All right, so if the first term is 3, the second term is 2 times 3, which is 6. The third term is 2 times 6, which is 12, and so forth. So here I've got a recursive formula for my geometric sequence, right? I'm using two different words here. One as a way to name the formula, the other as a way to name the sequence. All right, again, if I want the 473rd term, which is going to be enormous, by the way, it's going to take me a long time to get there because I'm going to have to keep multiplying by 2, multiplying by 2, multiplying by 2. So instead, why don't I try to come up with an explicit formula for this geometric sequence? There is a formula for an explicit formula here. It's a sub n equals the first term times that constant ratio to the n minus 1 power. And again, we'll make the same rules that for those n values, they have to be integers, right? I can't have a 4 1/3 term. That wouldn't make sense. All right, so if I want a formula here, my a sub n is going to be the first term, which is 3. That ratio value is 2 to the n minus 1. And we'll be very careful that we don't include the 3 on the inside of that set of parentheses, right? The 3 is on the outside, the 2 is on the inside, because that power only applies to that ratio of 2. All right, if you want to try it out for n equals 1, you'll get 3 times 2 to the 0 power, which is 3 times 2 to the 0 power is 3 times 1, which is 3. The next time you do it, you'll get 3 times 2, which is 6. The next time you'll do it, you'll get 6 times 2, which is 12, and so forth. You can have sequences that don't go up, right? My first two examples were both sequences that went up, but sequences don't necessarily have to go up. I could have a sequence that looks like this. My first term is 18. My next term is 9. My next term is 4.5. My next term is 2 1/4, and so forth. And so that sequence is also geometric, right? It's got a constant ratio, except that that constant ratio is a half. So you can have constant ratios that are less than 1. In this case, my ratio is a half, and I could write an explicit formula by saying 18 times 1/2 to the n minus 1. And starting with n values of 1, that would make sense. All right, what if I did this? What if I set up a sequence like so? I've got this sequence that goes 4, -12, +36, -108, ... and it just keeps going. So this sequence looks a little bit different from the other ones in that the signs alternate. So what do I do when the signs alternate? Well, if you want to find a ratio in a geometric sequence, all you have to do is take the term and divide it by the term before it. So you might say that the ratio in these sequences is a sub n plus 1 divided by a sub n. So if I wasn't sure what my ratio is here, pick any ones. Pick, let's say, the 36 and the -12, divide them, and I'll get -3. Or, if I wasn't sure, I could take the -12 and divide it by 4, and you notice again, I get -3. So those two ratios are the same. I could keep going all the way through. I'll find out that all the ratios are the same. So let's come up with this explicit formula. The nth term is the first term times my constant ratio to the n minus 1. Now, if I check this out, do my signs work out correctly? All right, so let's check the signs. The first term is going to be 4 times -3 to the 0 power, which is 4. Okay, so that checks out. The second term will then be 4 times -3 to the 2 minus 1, which is 1 power. 4 times -3 is -12. And I'll bet you if I keep going, a sub 3 is going to be 4 times -3 to the second. We're going to remember that -3 squared is +9. 9 times 4 is 36. And sure enough, my list matches up with the sequence that I was given. Great. So now we know how to write explicit and recursive formulas for sequences. What if it worked the other way? All right, in the second part, we're going to figure out what happens if I give you a formula for a sequence and ask you to write out those terms, and then give me some information as to how those terms behave as the limit of the term numbers begin to approach infinity.